meeting. Okay, today I will talk about the time of flight technique that many of you already know, and on the detection of high energy protons, laser accelerated protons with this technique. For who doesn't know about laser acceleration, and this slide, in the first slide, just showing what is the laser acceleration, what is the laser-based ion acceleration in contrast to the conventional technique. In fact, as you know, the ion acceleration is conventionally performed using very huge machines such as cyclotron, synchrotron, or LINAC, but that allow to accelerate a single species, a single unique species, using a very huge and expensive machine. The typical electric field in this machine can reach a value of about 50 megavolt per meter. But of course, to increase the energy that you want to reach, you have also to increase the dimension of the machine and the distance. The distance of particles. In contrast to this technique, recently there is another technique, which is the laser-based ion acceleration, as the name is. Said the name is based on the use of a high-power laser, which is focused on a target and on a solid target, as you can see here. And from the interaction of the laser with the surface of the target, you get an acceleration of different kind of particles in both in the backward direction and the forward direction. This is due to the creation of the formation of a plasma state on the target, and you get not only a single species, but you can produce different kind of particles, gammas, X-rays, but also electrons, protons, and ions. So in a single interaction, you can have different kind of particles, and but moreover, in this area, so in the area of the surface, a very big, very strong electric field is created, which is of the order of higher than 10 teravolt per meter, so it's very huge. And this acceleration is occurring in a very short distance of the order of a micrometer. So in contrast to a conventional acceleration, the acceleration is performed in a very small, in a very short space. Here I'll show you just the mechanism of interaction and acceleration for the acceleration regime, which is called the target normal shift acceleration. Because according to the intensity and the characteristic of the laser in terms of energy released in the target and pulse duration and the intensity, you can have different kind of different mechanism of acceleration. This one is the one that is more studied from the experimental and theoretical point of view, and it is dominating for intensity higher than 10 to the 18 centimeters square. And as already said, what is happening in this interaction is that you have your laser pulse. We typically have a very small, very short duration of the order of from picosecond up to tens of down to the tens of femtosecond. And when the laser hits a very thin target of the order of micrometer, it releases all its energy to the atoms that are present on the surface of the target. Due to this interaction, a plasma is created on this area. So plasma, it means that negative charge and positive charge are separated. Electrons that are the lighter particles are immediately emitted in this direction, And due to the charge space separation between negative and positive particles, you have in this area, you have a very strong electric field, which is the one responsible of the acceleration of protons and ions. Typical protons are in fact present in the target as contaminants because we are talking here about metallic or plastic target. Also, the beams that is coming out from the target is typically is a pulsed beam because it's accelerated in a very short duration, and have characteristic and so feature very different from the conventional one. In fact, the proton beams, the protons that are accelerated with this regime, with this mechanism, have a very wide energy spectrum. This is a typical spectrum coming out from this kind of interaction. Is a continuous energy spectrum, typically is exponential, decreasing exponential, and with a cutoff, so a maximum energy, which depends on the laser and the target characteristics, mainly also depending on the high intensity of the laser. In contrast to the conventional acceleration, you don't have a monoenergetic beam, but you have a polyenergetic beam. So it is very different. Another peculiarity is also the divergence. In fact, you have a beam very divergent, which can reach also a value of 20 degrees, plus minus 20 degrees. And usually also the angular distribution is dependent on the energy. As you can see here, the more energetic particles, protons, are emitted in a smaller cone around the direction perpendicular to the target, and the less energetic particles can reach also higher divergence. But for our for this talk, the most important the most important characteristic of these beams is their intensity. In fact, in contrast to the conventional beam, we can get in a single interaction a very high number of protons, of the order 10 to the 10, 12 protons in a very short pulse duration, which means that we have a very high dose rate and current beam. So all these characteristics of beams that are very far from conventional ones make necessary the development of specific diagnostics and specific detectors for the diagnostics of this beam. So in this slide, I just reported what are the established technique used in laser-driven experiments. And the first one is the Tomson Parabola spectrometer. So, you know, but just giving an overview. So it is composed by a magnetic field and an electric field. And the coupling, so magnetic and electric field, as you know, you can distinguish between the different ion species, in particular the charge species, because you can discriminate them according to the ratio between their charge and the mass. After the magnetic and electric field, you put, in fact, you can place a detector at a certain distance from the electrode and separate the different track according to the ratio, the charge mass ratio. Typically, this kind of detector could be, for instance, a microchannel plate or image plate. In the case of the microchannel plate, you can have all these, the discrimination, so of the track online, so real time during the experiment. And so this is a very nice technique because you get basically everything. You can identify the different kind of ions that are accelerated. You can get the energy because if you have your system calibrated in energy, you can have information on the energy and also on the number of particles. Then there is the time of flight detector that I will describe later in details, and other kind of detector that we call passive detectors, because they need they need a post-processing of the measurement to get the information. They are, for instance, as you already know, the radiochromic films that are in this kind of application, this kind of experiment that are they are typically used in a stack configuration, as you can see here. So placing different layers of RCF close to the target, so that you can measure the beam spot, so the whole beam. You can have information on both the spot, so the shape of the beam, the dimension of the beam, but also on the energy, according to the different layers of RCF that particles can reach. So in this way you can have both, again, the shape, the dimension, the size, but also the angular divergence, according also to the energy. Other kind of passive detector, of course, are the nuclear track detector CR39. You can see here a picture. So each point here is a track, so they are track detector, in fact, because each point or each particles produce a damage in the material. You can count them, and if you have a calibration, in energy, you can also perform a spectroscopic analysis and get the measurement of the dose, because you have the number, the flux, you have the energy, the kind of particles, and you can get the dose. Now let's talk about the time of flight technique. So how it is used. You have your laser, which is hitting the target, and then you place the detector at a certain distance from the target, detect the signal, and this is typically done using a fast oscilloscope, which is oscilloscope, and without using any amplification, because as already said, you have many particles in a very short time, so you don't need to amplify the signal, as is commonly done with conventional beam. This is a typical signal obtained with laser-driven beams. And so you can see, typically we have a first peak, which is called the photo peak, because it is arising from the X-rays and the gamma rays that are immediately emitted from the target when the laser is hitting the target. So it gives you the T0, so the moment, the instant when the laser is interacting with the target. Then after this, you have, of course, the immediate emission or acceleration of protons. And after that, according to the specific experiment, you have ions. So this is like the time evolution of the beam. And of course, the x-axis is the time. The time for time is the time of flight, because it's the time that particles need to reach the detector. So if you know the distance, you know the kind of particles, you can have you can measure the kinetic energy of the particle itself. Regarding the detectors, yeah, this technique, the time of flight technique, was already used at the beginning, many years ago, with very low energy beams. Typical detectors that were used were Faraday cap, ion collectors, and secondary emission monitor. But this kind of detector, they produce a signal which is typically proportional to the number of particles, to the charge. So you don't have an amplification, a natural amplification. And so it means that the signal to noise ratio actually is very low. So in experiments when you have a very huge noise, electromagnetic noise, and a few number of particles, this kind of detectors are not suitable. And also they have low time resolution, and the signal is very, very slow. So for this reason, this kind of detector are not cannot be used for extremely high energy proton beams. That's why that recently, also in our group, as you know, we use different kind of detector that are semiconductor-like detectors, so silicon carbide and diamond detectors that are have many advantages for the detection in particular of high energy protons, laser-driven protons. In fact, they are very fast, have a very good time resolution, and the signal is not only proportional to the number of particles, but is proportional on the energy released in the detector thickness. This means that we have a very high signal-to-noise ratio, and they have good performance also in this kind of environment when you have extremely high electromagnetic noise, and are the one that are currently used for the detection of high energy laser-driven proton beams. When I say high energy, I means energy higher than 10 MeV, of course. So this is just to show you the previous work done for the ELIMED project. And in fact, when we were looking for the detectors for the ELIMED beamline, these were the requirements. So these are requirements. So for the detection of particles, so of course you need detectors that are able to sustain a very huge current. So the order of 10 to the also up to 10 to the 12 particle per bunch. You need a high time resolution of the order of 100 of picoseconds, and a small capacitance, low capacitance, and to have a very small noise. That's why at the end, we selected diamond detectors. In this case, we had two different kind of detectors with 100 and 500 micron of thickness, and a small capacitance of 4 picofarad. These detectors were also tested with the conventional proton beams here in Catania at 0 degree. And this was an experiment performed in time of flight. Maybe if you want to discuss about that later, we can discuss. And
this is the difference between in time.
Yeah, no, we had two detectors. There was a start and a stop in transmission with 60 MeV protons. And we measured about, yes, this time resolution. So then let's talk about the signal processing. So again, this is a typical time of flight signal. You have time of flight and amplitude. And what is typically done in this application, when you know the kind of particles, for instance, in this case, we had only protons, you can try to deconvolve, to reconstruct the signal using typically this kind of function, which are called Maxwell-Boltzmann shifted functions, which depends on two plasma parameters, which are called shift velocity and the ion temperature. So varying these parameters, you can have different functions and try to overlap the signals to reproduce the signal. Okay, yeah, this is for the amplitude, but in semiconductor-like detectors, so diamond, silicon carbide, and so on, the amplitude of the signal, as already said, is depending on not only on the number of particles, but on the energy lost inside the detector thickness. And so from the measurement of the amplitude, you can convert, you can convert this axis, the y-axis, in the N and D using this formula, which depends, of course, on the energy, the real energy released in the detector. Yes.
In the deconvolution, no? You don't need the absolute number of particles.
No.
No, but I mean the height of each curve, from which parameter?
It's arbitrary. Yes.
Exactly.
It's something
But
that you have.
That VI that is on the sum. What you change to get the correct height?
I change this, and the amplitude.
The amplitude. But so the height is the amplitude.
No. This one is the amplitude of this, then of this, of this.
Yeah,
but I change the amplitude.
You change, but to
so that the sum of these functions is overlapping the signals.
Exactly.
Is that?
No, but the only parameter for the amplitude is VI.
Yes. Yes, okay. Because this is NT.
It is fixed, no? What is T?
T is the time.
T is the time. L is the length.
The distance.
The distance. So to get the correct height, you change VI. So VI is another parameter. I mean,
is the amplitude. Yes, but it's not depending on physical quantity. It's
no,
just
no, because it depends on the
factor. It's a factor.
Yeah, but when you make the convolution, you have an automatic procedure to change this VI, or you make it
by hand. Yes. But you can, you can, if it's possible to implement something that in polyfit.
There is also polyfit. But Calendar is a very powerful deconvolution algorithm. I mean, there are many algorithms. Okay, so the parameter in total are 3, not 2.
Yes.
Q depends on the physics. One.
Yes.
It's related to the amplitude that depends on the number of particle energy is inside.
Yes.
Okay.
Yes.
But why the temperature is different for the different problems?
Could be different population.
Is energy, but also the velocity is velocity of temperature, because you say that we change the temperature and velocity to fit different curves.
This.
For example, you have a different curve for 10 MeV proton, 9 MeV proton, and so on.
Yeah.
But temperature and velocity are similar to energy. Is something that is connected to the energy of this particle or not? Temperature.
No, so the velocity, the shift velocity. With the shift velocity, you change the energy actually, because the particles. The temperature actually is the width of each curve. Yes.
Because because that one is the temperature of the plasma.
Yeah. In fact, is not fixed, but is more or less the same for all the one. Yeah.
But one, yes, one. But depends on because the plasma is expanding. So there are parts with different.
But everything is coming.
The velocity is different because you have expanding the plasma.
There is only one temperature in the plasma.
Usually is the same. But the shift velocity is
but you change a little bit also the KT factor.
The
KT, the
temperature.
You change a little bit this factor.
Yes, but to fit better the signal, but it's more or less the same. The shift velocity, no. The shift velocity is
depends on the energy. So the most important parameter is the velocity of the.
Yes.
The velocity that is connected to the energy.
Yes.
Yeah.
But you change the temperature, for example, in different shots.
Yeah.
Because we have different energy on the target.
Yeah. Shot by shot.
So the temperature is a fit parameter.
Non si sente, no.
Is a
fit parameter.
non.
Ha detto fixed, credo, fixed.
Fixed,
no,
the temperature, no.
The temperature is a fit parameter.
Fit.
Yes.
Yes.
Ok.
Non si sente piano. È in italiano. Vabbè.
And if you want to know which is the number of the particle with different energy, you have to take into account on the number of the protons that interact with your detector and also the energy of these protons.
Yes. Yes. Not only the energy, but also the real energy loss inside the detector thickness. We'll see that.
And if you have in transmission detector, you have to take into account
this
detector
thickness and yes, estimate the real energy loss. Yeah. In fact, you have the kinetic energy is measured in with the time of flight. So in the x-axis you have the kinetic energy. So using the normal equation. And then if particles are stopping inside the detector thickness, this value here is exactly the same as the one, the one given by the time of flight values. If the particles are not stopped, you have to calculate the real energy loss starting from the kinetic, this information, so starting from the kinetic energy. And this is what I implemented for the thesis. So if you have a signal like this, so this was a signal from RAL, and so here I was sure that protons were not stopping inside the detector, so the detection was in transmission. So starting from the time of flight, so from the kinetic energy, I wanted to retrieve the energy loss inside the detector thickness, and so I performed the simulation. So the purpose was to obtain a relation, a sort of function that allowed me to pass from the kinetic energy to the energy loss point by point, because it's not more energetic.
And the band is due to the statistical fluctuation.
Yes, because Monte Carlo.
So if you increase the number, you get the
yeah. But then this one, the light blue line is a fit. I used only the fit.
But when you calculate delta E, you do not consider this error.
No, I use this one as error of on the number of final number of particles.
You include this error.
Yes, because it's an error on the energy loss.
On the calculation.
Yeah, only this. So using this in this way, so with Monte Carlo simulation, you can convert the kinetic energy in energy loss, and so convert at the end using this formula again. So replacing here the E with the energy loss, you can calculate the then in the E in this way. So this in this case is taking into account the real energy loss in the specific detector.
For a given particle.
Of course, here we are assuming that we have only protons. You see here is protons. When you have protons and different kind of ions, you can't distinguish the different species. So also for the kinetic energy, you don't know what is it. And this is a limitation of the time of flight technique, actually.
And also the unborn.
Yes.
Okay, so basically you apply this formula
only for a specific kind
until
of.
you are sure that the species.
No, for instance, I will show you an example. For instance, the experiment in RAL.
Okay.
What was done also for try to distinguish between protons and different ions.
Okay.
So here is an experiment. The first experiment we performed in 2015 in RAL with the Vulcan petawatt laser. So we had a very, very powerful laser with this characteristic. This was the target, was 25 micron of aluminium. Laser hit the target, and we placed a detector in this direction, in the backward direction. Was again a diamond detector, and we also used a Tomson parabola spectrometer close to the diamond detector to cross-check and to validate also the technique. And now I will show you what we did. So this was, for instance, the signal we get in this position here from the diamond detector. So this is the photo peak, then we had the first peak and a very huge peak. So we didn't know if we had the protons or carbons, because time of flight is not possible to say anything at this stage. But thanks to the Tomson Parabola spectrometer, which was placed more or less at the same angle, we knew the type of particles, so that we had protons and carbons and oxygen ions with different energy. And again, thanks to the Tomson Parabola, we had also information on the maximum carbon energy. Because if we know the maximum carbon energy, which was 4 MeV per nucleon, we can say which corresponds to this line in the time of flights, which it means that the signal that is coming before this time are only protons, because they're not carbons and ions.
At that energy.
At this energy, yes. At this energy. And this is possible only because we had another diagnostics that gave us in the maximum carbon energy. Because otherwise we could, the maximum carbon energy, which corresponds to the minimum time of flight where you expect to have carbons.
Okay. That is this blue line.
Yes, it's this blue line. This one corresponds to the time of flight of 4 maybe per nucleon carbons. Yes, means that particles coming before could be only protons. They cannot be.
But why there are these 3 peaks, for example?
Bella domanda. It could be different population of protons. These are protons. Protons. This one.
This seems that there are 3 different levels that are excited in the plasma. How is treated this?
No. First of all, this is the time of flight signal. So this one, when you convert this in energy spectrum, they're not numbered because they again you have to convert the amplitude in energy loss.
Sure. But you have the corresponding spectrum.
Yes, this one.
Okay. So there is no peak.
No, it's a continuous.
Okay.
Yeah.
Sure. There is a null.
Yeah, because in this very small region we had protons and carbon ions, so I couldn't reconstruct.
And then again protons.
Yes, because we had the absorber, we had different filters in front of detectors that gave us information on the minimum energy of carbon ions, because the filter were stopping.
So
ions.
Carbons are only in
on
that
this
window.
Yes.
Between red and
I can't say anything in that region because it's very small. But probably they were not carbons, but according to the calculation,
But you
I removed this.
A signal in the right side of the plot.
Here.
No.
Here.
Yeah.
This one.
Yes, because it's different to 0 there.
This one. Yeah. This one is probably is not physical. Could be the discharge of the detectors, because according to the filter cut, protons should stop here. We shouldn't see anything after this.
With the filter, depending on the filter.
Yes.
And look into the maximum energy of protons, you see these protons have to stop there.
Yeah, I mean this time of flight value here corresponds to the minimum energy of protons that pass.
The minimum energy that you detected with the Tomson parabola, or
no?
No.
You have the field.
Okay. Let's stop. Okay. Understand.
Yes, it could be the detectors, or could be also the effect of the filters, and some particles pass and comes after this point.
But what about the oxygen? Because you mentioned several times about the carbon ions, but what about the oxygen?
Oxygen, of course, they, as you can see here, had lower energy than carbon. So of course they could be here in this region here. Not of course in the region where the protons were present, because they are heavier ions than carbon ions, so they are typically accelerated with lower energy. Okay.
Okay, thank you.
Because again, here it's written here, in fact.
Okay, coffee break now.
Coffee break. Coffee?
No.
Not bad. Again, this was another. Okay, this is nice because when we put the demo detector just close to the pinhole of the Tomson parabola spectrometer, so they were more or less at the same angle, at the same distance, we could.
This is the same scheme that you showed.
No, it's a bit different. Here the time of flight was farther.
Okay.
Here was closer. Yes, it was on the Tomson parabola pinhole. And so basically the time of flight and the Tomson parabola were looking at the same beam. So we could compare directly the energy spectrum from time of flight and the energy spectrum from the TPS. And this was the comparison. The blue line is the demo detector and the TP is the black line.
The TP was calibrated in energy.
Yes.
But was an image plate.
Image plate. There is a publication done from, I think, Domenico. They published the calibration of the image plate with protons in the same energy range, so that they could give us the absolute number of protons. These are comparison of number of protons and also maximum proton energy for different shots. Only these shots, actually. And you see more or less that you can see that the trend is more or less the same for both the diagnostics, not for this. We did also comparison with other diagnostics, with radiochromic films, STAC and CR39. These data are not published. Actually, we published only the Tomson parabola once. Again, as we always do, we use the different thickness of filters. In this case was copper, but the CR39 was very long. So actually the different part of the CR39 were at different angles, because it was like this.
But just one shot, please.
Yes, one shot, for sure. And this is the plot. You remember we talked about this? Yeah. Because this is the number of track corresponding to the different cut, so to the different filters, and the comparison.
But there is an angle dependency.
Yes. Yeah. It's difficult. It's more difficult here to compare time of flight to CR39, because the time of flight is a point.
Yeah.
CR39 is huge.
Use a system like the one we used at Pulse with.
I don't know. I don't remember why we had this very long CR39 stripe. It was a stripe. It was at the beginning. Then this was. Yes, Rosanna did. And the first CR39 that were brought.
I remember the light.
The light?
The center.
In the center of the CR39.
Yeah, yes.
Yes.
Yeah. Brute. Yeah, and then this was another measurement performed in the forward direction. So we were expecting to have a higher energy, because here we had 20, 19 MeV. In the forward direction, they were getting 40 MeV. So
the
for
target is the same.
yes, yes, was always the same. So for the last two shots of the experiment, we placed the diamond detector in the forward direction, and but here we hadn't the Tomson parabola, so we just assumed that carbon ions, the maximum energy of carbon ions was 10 MeV per nucleon. This assumption was done according to publication done from the Queen's group in the past, but experimentally we couldn't have this information. So this means that in the signal, in the time of flight signal, only this part we were sure that was arising from protons. So only this part was analyzed, and this was the energy spectrum from protons, which was measured. So with a cutoff of 31 MeV. And we also could compare this spectra with the radiochromic films placed always in the forward direction.
It's good.
Yes, it's very good. Yeah. The comparison is good. In fact,
34 nanosecond corresponds to the 30 MeV.
34, yes. Yeah, at this distance, at 2.5 meter. So this was very nice experiment, because we actually validated all the technique and the procedure and the analysis in both direction. Yes, and also this come back. This one was nice because actually the detector here was very close to the target. It was about 1.2 meter, which is close because we had 20 MeV, and the time of flight was 20 nanosecond. So this means that this technique can be used also in very short distance. You can resolve.
But why at pulse we stay so far from the target?
The pulse, the problem is the very high energy, noise, electromagnetic noise.
If you stay
too close to the target, you can get more electromagnetic pulse. Yeah.
So not so.
Of course, this depends on the detector, because here the photo peak is very small. So if we add a huge photo peak like this with a very long tail,
then there is a problem for the signal.
Yeah, there would be a problem on the maximum proton energy detection.
In this case, you're sure that
no, because the diamond detector had this performance, and we could go very far. Yeah.
And the silicon carbide?
No, silicon carbide.
Just diamond.
Yes. Yeah. We had only. Yes.
No,
Yes.
my question is you have data from silicon carbide.
We had one silicon carbide, but we didn't analyze.
From the measured pulse. I mean,
No.
we have a photo peak, in the silicon carbide.
Yes. It usually is higher and longer. Yeah. These are only diamonds.
Because they get
Sorry, but
for the diamond, you have an higher.
Sure, each detector is a different behavior.
it depends on the thickness also, the dimension. These were very small, very small size detector. The capacitance.
For the sample, you can use the sample in time of flight configuration if we want to distinguish the photons with protons. Because we use the sample just with the charge integrator. Blah, blah, blah. And in this case, you cannot distinguish different particles. But if you use the sample in terms of flight configuration, you can suppose that there are photons, protons, and other things, no?
It depends if you are able to see photons.
Yes, because
it seems.
Yeah. In Pisa,
but if you use it in time of flight, you don't have amplification, right?
Without amplification.
Yeah. So depends if the signals are comparable between them. So the signals from photons and from protons and ions, like here. No?
No, but because in Pisa, if you remember.
Yeah, but with the amplifier.
Yes.
It depends on
Just
how
see
the
the
reaction.
signal with the photons. If you stop the photons and you see the signal is similar to the
But the
photon
problem
or not.
in
Just to
PISA,
see.
Yes, yeah.
in PISA, the problem was that we was not able to connect without the amplified the signal. Why we don't use the?
No, because we didn't do. Che avevamo tutti in borsa. No, non l'abbiamo.
This we could connect to the same bias T of the silicon carbide, also the same. And if the signal is strongly,
Non lo so,
The same, no, because the capacitance is different. You cannot use the same.
I don't know.
I don't know.
But you don't need to
No,
to
yes,
give the
because you don't
voltage.
have a bias.
No, directly the cables in the oscope. Without bias.
Not the bias.
No.
But because there are paper on SAM,
Yes, yes.
we can just see.
Daniele show
Yeah.
Che poi io conoscevo l'articolo.
Io non lo ricordo,
Sì,
ma io
sì.
ce l'avevo.
A posto.
Sì, no, scusami, no, ero in Corea, perdono.
Goreva?
No, ho sbagliato. Una volta l'ho lavorato per tutto, cioè quella al pass. No.
Bertuccio.
Because if we have the contamination of the photons, we cannot have any information about the dose. Yeah, so dose of the product, because you have the contamination. This is the problem.
Mhm.
In the sense. We don't know which is the dose.
Eh,
The dose due to the product.
esatto.
Not only
It's something that we have to evaluate if
But not
the contribution of photons in
But
the.
not only with them. With
Yes.
any detector that is sensible to both radiation,
Yes.
you
Yes,
Probably
but
you
when
use-
you use in time of flight,
Yeah.
You distinguish in time.
Yeah.
could,
When you have the integration,
sure,
no.
you can really
But we can have in this way information about the contamination of the photons. The
It
content.
depends if the signal is strong enough to be detected with something.
Yes.
And this is the reason why we use the Faraday gap, because it's not it does not depend to any other radiation other than charged particles. But if there is a radiation and cells are there,
Yes, the cells.
no, but you can use the Faraday gap to distinguish.
Yes.
Because in principle, if you have a detector that has only charged particles, if there is a gamma component, you can discriminate this, trying to subtract.
Mm.
No.
But also with the gaptromic, we don't know exactly which is the spectrum of these photons, because probably also with the gap, we have a cut.
Yeah, but
Yes.
if you have the radiochromic calibrated in protons,
Yeah.
if you have the Faraday gap to give you an absolute independent value of the dose,
Yes.
with if you compare this with the radiochromic, if the radiochromic you find a bigger dose, then you may have the dose to the X-ray.
But are you sure that with the radiochromic image you see all of the photons that are preserved or not? Because the cells see everything, but the radiochromic does not. This is another.
But this for element.
For element,
But you think that at the end of the beamline you get the X-rays?
Yeah, because we are at 0
We
degrees.
don't
Because it's 0 degree.
How much?
We have to change the position of the particles.
Sarebbe una cosa da
You
fare.
have to check.
Because for instance, with the dipoles, you don't have this problem. 0 degree, you are not at 0 degree, you are an angle.
So the gamma component.
You have we have LED shielding, everything, but you don't. At least you can control this. Yeah.
Okay.
But in principle, we can try to use similar condition also in PISA. For example.
With
For
the dial,
other, yes, for the other experiments in the future, we can try to
Yes, 20
investigate
years.
20 years. Yes, Luca.
Finish?
No. This was I don't know if you have never seen this. This was another experiment in RAL. We performed with the Queens and the Eli. was with the cryogenic target. So you can get with this technique develop Grenoble, pure hydrogen ribbon target, which is produce a continuous flow of water, of cryogenic water. This means that you can get only protons. You don't have contamination of ions. Hydrogen, pure hydrogen. H2 is the molecule. But the advantages of this target is that you have only protons. The acceleration, the particle accelerated are only protons. So the time of flight technique again.
And electrons, no? I mean,
Electrons, yes.
You cannot see electrons.
Electrons are in the photo peak, are here.
So the velocity is the same.
Are because they are very fast, they're very energetic, and they reach the detectors are very short time.
Okay.
And the signal is usually is the final tail of the photo peak. Yes, and sometimes you can see a second peak. You can resolve the second peak depending on the distance. And I think that silicon carbide are more sensitive to this. I saw some more structured signal. Yes. So in this case, where we had only protons, time of flight technique is perfect because you can really use this to real-time diagnostic detect the protons.
Like we did in Pisa.
Yes.
Yes. Pisa, because we are
Exactly.
sure that there are only protons.
Here we had very high energy, also 50, 60 MeV, and in a very short distance. Again, here we had a flight path of 1.5 meters. So again, we placed detector in different direction. This was forward direction. This was backward direction. And real time, we had the possibility to convert the signal in energy spectrum, have this kind of results. I don't know when Daniele will publish this data.
Because they are not still published.
No, not yet.
And why?
Because yeah. But no, for the demo flight, because there were many diagnostics in this experiment. 4 Tomson parabolas, calorimeters, many things. And so I think that they're starting, Daniele is starting to write the first paper. Because this target was for the first time tested at pulse,
Yes.
but there is already a publication about this, but was very low energy, 1 MeV.
Sure.
But they, one, yes. But it's clear that with this target you have only protons, and also number of protons is higher than plastic normal conventional target. Yes. In principle, this technique is could be good, could have a good potentiality for a high repetition rate because you have a continuous flow. But they need to improve the technique because with this laser, where Vulcan laser is a huge, is a petawatt laser, so we had 600 joule in 500 femtosecond. And so actually what happened that when we shooted all the system was increasing the temperature, so we had to wait 4 hours before shooting again.
No,
Yeah.
4 ore.
Sì.
Because it's
complicated.
It's a cryogenic system, so it's at very low
Yes.
temperature.
Yeah.
So
Everything was
500 joule, 500 joule.
500 joule.
Sorry, general question. Maybe I lost this information at the beginning of your presentation. In which way the angle between the laser direction, the target, affect the producing plasma?
Bella domanda. Chiamo Daniele. No, usually
there is an optimal.
no, depends. No, it's not fixed for all the system. Usually, it's not perpendicular. It's not perpendicular to the laser. Is not perpendicular. Usually, is could be 15 15 degree, yes, between 10 and 15
But it's
degree.
not perpendicular for a safety reason.
Yes.
Not for the.
Yeah.
Because you have a component.
The reflection of laser.
Okay.
That can enter in the optics again and come back to the laser and destroy it.
Destroy the optics.
So you,
Yeah.
because a given component of the laser is reflected from the target, not on
Yes, of course. But
Like
why,
a mirror.
Why you use, for example, 15 degrees and not 30 or 35?
I don't
Or
know.
less.
Or less.
Yeah.
Okay.
I don't know.
I don't know if there are systematic studies on this.
We can ask for that.
Huh?
We can ask for that.
Leo.
Daniele should know this. Okay, perhaps this dependent is not so strong because I never saw studies on this, but okay.
I don't know. For instance, for example, at Pulse, we were shooting at 15 or no, 30,
No,
30
degree.
30 degree.
30?
Yes.
30 degree.
But it was done to increase the target thickness,
The target thickness.
more or less.
Yes.
If you increase the angle, you have to increase the thickness.
Yes.
Yeah.
Because you touch the thickness again.
Because it's oblique. So to increase the
But
number of reaction.
The number of reaction.
Mi
But,
fatto pensare una cosa.
There is
but sometimes
Che il target non è, che il target è più spesso di quello che pensiamo.
Esatto. Che non torna il numero, perché in realtà effettivamente se sta a un angolo vede di più. Effettivamente questo potrebbe spiegare tante cose.
Grazie.
But this may be not optimized for the acceleration because
No.
there is a thickness, ideal thickness of acceleration depending on the laser time duration. So in general, also in Pisa, no, they did these studies of acceleration changing the thickness of the target, and you with the TNSA.
We fix an angle.
We fix the angle, and with the TNSA you see that there is a ideal thickness to get the maximum energy, for example.
Energy or intensity?
I don't know. Probably yes, because if you get more energy, means that you was able to deposit more energy from the laser. Because the problem is to, as far as I understand, to try to deposit the maximum energy of the laser inside the target. Because you lose a lot of energy. You have this incredible intensity, but you
It's the conversion of laser
the
energy.
The conversion efficiency is very low. So
It's
you have to
5%.
maximize this. When you maximize, you create more plasma, more energetic plasma. Plasma is the same, and probably more flux of particles.
Both.
But
Both.
we have applied for Vulcan, no? For the proton bomb, Lorenzo.
Ah sì.
Yes.
No, ma sì, è Vulcan.
Right.
Però
Ma quanto tempo fa?
l'altra
6 months.
non is not this
Was Gemini.
target area.
Was Gemini.
No, was the laser is the same, but is the other target area, TA West.
6 months ago, more or less.
But now this green time was seen or not? We are waiting.
Yeah,
Is
we're-
it started?
So,
6 months, we are waiting. 6 mesi.
no, probably they had